Hello everyone, this is Lakshmi Sindhu from second year ECE. In this, I will discuss about finite state machine and introduction to finite state machine, limitations of finite state machine. In this, we have two different types of finite state machines. One is Moore machine, second one is Mire machine. Comparison between Moore and Mille machines also we will discuss, and analysis of clocked sequential circuits and design of clocked sequential circuits. Finite state machine. A finite state machine is a mathematical model widely used to describe and control the behavior of systems that operate in a limited number of distinct states. FSM means finite state machine consists of a specific set of states and transitions between these states like inputs and outputs. We have some components. One is states, discrete modes representing the system's condition, and transitions, the movement from one state to another state in response to inputs or events. Inputs, external signals or conditions that drive transitions. Outputs, result based on the current state or the current state and input. Limitations of finite state machines. First one, limited memory. Finite state machines cannot handle systems that require unbounded memory. It can handle only some of the bounded memory. And second one, state explosion. As systems complexity increases, the number of states grows exponentially, makes the finite state machine hard to design. It is very difficult to design the finite state machine if the number of states increases. Third one, difficulty in handling infinite inputs. Finite state machines work only with discrete inputs and outputs. It can work with only some inputs and some outputs. Fourth one, inflexibility to handle dynamic changes. Finite state machine behavior is fixed if once we design the finite state machine. Fifth, not suitable for high complexity systems. For large scale or control systems with many interacting variables, FSM becomes unmanageable and error. Types of finite state machines. Finite state machines are classified into two types based on how their inputs are generated no, sorry, how their outputs are generated and how they handle transitions. First one, Moore emission, and second one, Mill emission. Moore emission. For this finite state machine, the output depends only on the current state of the machine, that is Z equals to F of Q. In this, Z is output, Q is current state. Mill emission. For this finite state machine, the output depends on both current state and the input. The input is may be either x or y. Z is equals to f of q comma x, where Z is output and q is current state and x is input. Here, the Moore machine is depending only on the present state of the input, and Melee machine output is depending on the present state and the present input. Comparison between Moore and Melee machine. Moore machine. In Moore machine, the output depends only on the present state. Melee machine, the output depends both the present state and the present input. Moore machine has more states than Melee machine. In Melee machine, only fewer states contains. Moore machine In Moore emission, the value of the output function is a function of the current state and the changes at the clock edges whenever the state changes occurs. In Mill emission, the value of the output function is a function of the transitions and the changes when the input logic on the present state is done. In Moore emission, more logic is required to decode the output, resulting in more circuit delay. Melee machine reacts faster than the Moore machine. The state table represents the relation between input, output, and the flip-flop states. It consists of three columns. One is present state and second one is next state, third one is output. The present state specifies the state of the flip-flop before the occurrence of a clock pulse. Next state is the state of flip-flops after the application of a clock pulse. Output. The value of the output variables during the present state. Here, the present state is AB. We have 2-bit number that the possible inputs are 0, 0, 0, 1, 1, 0, 1, 1. The next state can be classified based on x equals to 0 and x equal to 1. The output y can contain x equals to 0 and x equal to 1. If x equals to 0, the next state values are 0, 0, 0, 1, 1, 0, 1, 1. And if x equals to 1, the next state values are 1, 0, 0, 0, 1, 1, 0, 1, 1. And output when x equals to 0 is 0, 0, 0, 0. When the output when x equals to 1 is 0, 0, 1, 1. State diagram. State diagram is a graphical representation of a state table. Each state can be represented by a circle, and transition between the states is indicated by directed lines, that is, arrows connecting the circles. The directed lines are labeled with two binary numbers separated by a symbol called as slash. The input value that causes the state transition is labeled first and the output value is next. Analysis of clock or sequential circuits. The analysis can be done by using the following block diagram. First of all, we observe the logic diagram and then we identify the type of circuit, either that is Mealy or Mole circuit. After identifying, derive the excitations, equation or Boolean expressions, and then derive the next state and the output equations from the excitation equations, and then generate the state table. After generating the state table, generate the state diagram by using the state table. Generating the state diagram indicates that the analysis has completed. By understanding the analysis, we will discuss one example. The state table and state diagram for the following sequential circuit. Here, the circuit output is depending on the present states only. If the output is depending only on the present state, then the circuit is called as Moore machine. Step 1. We have to identify the type of circuit. The output Y of the circuit depends only on the present state. So the logic circuit is the Moore type machine. Step 2. Excitation equations. Flip-flop input equations. For flip-flop A, JA is equals to B, KA is equals to B into X1. For flip-flop B, JB is equals to X1, KB is equals to AX, Y is equals to AX or B. Step 3. Find the characteristic equations of the flip-flop. Here, an plus 1 is equals to J into Qn bar plus K bar into Qn. Here, Qn is equals to an plus 1 is equals to B into A bar plus B into X bar whole bar into BA bar plus A into B plus X. BA bar is equals to AB bar plus X. An plus 1 is equals to AX or B plus X. State equation for flip-flop B. Bn plus 1 is equals to X bar B bar plus AX or X whole bar into B. X bar B bar plus AX plus A bar X bar into B. Bn plus 1 is equals to X bar B bar plus AXB plus A bar X bar B. From the excitation equations, the state table can be represented as the following: present state, next state, and output. Present state AB 00011011. If x equals to 0, the next state AB becomes 01111100. If x equals to 1, the next state AB 00101011. The output y equal to 0110. By using the state table, we have to draw the state diagram 0 0. If AB equals to 0 0, when x equals to 0, the output is 0. Here circle, inside the circle you have to represent the present state divided by the input. The output is representing to 0. Remaining all the cases have to represent the by using the state table. And design of clocked sequential circuits. We have to follow the following procedure to design the sequential circuit. Step 1. Obtain the state table from the given circuit information such as a state table or description. Step 2. The number of states may be reduced by the state reduction technique. Step 3. Assign binary values to each state in the state table. Step 4. Determine the number of flip-flops required. Step 5. Choose the flip-flop type to be used according to the application. Derive the excitation table from the reduced state table. Step 7. Derive the flip-flop inputs and outputs using K-map simplification from the above step 6. By understanding the design of sequential circuits, we'll discuss one example. A sequential circuit has one input and one output, and its state diagram is shown in the figure below. Design a sequential circuit Mealy machine using D flip-flops. The state diagram did not have any equivalent states. The number of states in the diagram have 4 states. It requires 2 flip-flops which are named as A and B. The present states AB and the next state if x equals to 0 and x equal to 1. Output when x equals to 0 and x equal to 1, we will get the following outputs. And the state diagram can be represented by using the state table. By observing the state table, we can conclude that the following state diagram indicates that Mealy machine. For the design of a circuit using D flip-flops, we need the excitation table of the D flip-flop and the circuit. The excitation of D flip-flop can be represented by present state, next state, and flip-flop inputs. Present state equal to Qn, next state equal to Qn plus 1, flip-flop input D is equals to Qn plus 1. The outputs which is having Qn plus 1 is equals to the output D. Qn plus 1 is 0101 and the input D can have 0101, and the excitation table of the flip-flop can be represented by using the excitation table of the D flip-flop, and finally the output gets as 01001011. The flip-flop input functions and circuit output functions are obtained by using K-map simplifications. By using K-map, we can get the input equation of flip-flop A, flip-flop B, and the output equation. The input equation of flip-flop A is A XOR B XOR X, and the input equation of flip-flop B is A bar B X bar plus A B bar X, and the input equation of and the output equation of Y is Y equal to A X bar plus A bar X. A sequential circuit using D flip-flops. we have to design the Mealy machine by using the following ex- input equations. By observing the sequential circuit, here the output is depending on the present state and the present inputs. Thank you.